Hi there. This is about identifying anyonic topological order in fractional quantum anomalous Hall systems. It's an overview of a preprint that we posted a couple of weeks back of the same title, which meanwhile got featured at Quantum Zeitgeist, who wrote a decent summary of it, which you can find online. So let me explain. Fractional quantum Hall systems first, without the anomalous. What are they? So we're looking at an electron gas that is in some way or other confined to an essentially two-dimensional superconductor, surface which I'm going to denote sigma 2, subject to a transverse magnetic field, indicated here by the field lines through some surface. Well, it makes it a fractional quantum Hall systems if there's a rational filling fraction of electrons per magnetic flux quanta. So in this cartoon here you see a single electron paired or associated with a fixed number of quanta of indivisible units over the magnetic flux by some slightly mysterious mechanism, which however is observed in experiment. So on the backdrop of such a fractional filling, every further surplus flux quantum is like what's called a quasi-hole or vortex in the background sea of these coupled electrons, meaning there's an electron missing here, or actually 1/k of an electron missing here, and there's a little vortex in the electron gas. So remarkably now, this is borne out by experiment very clearly, and in theory it's kind of sort of understood. These surplus magnetic flux quanta are solitonic anyons, meaning that as their world lines are being braided, so as they change position in this fashion here, the whole system picks up, its quantum state picks up a complex phase depending on this filling fraction. The point being that this phase is actually dependent only on the global topology of this process, not on how these paths wiggle. In this sense, this phase transformation is insensitive to local noise and hence could in principle implement what's called a topological quantum gate, a noise resilient operation in a quantum computer. As such, there's a huge interest in understanding and getting control of such topological quantum gates. So here's that phase. Now, as I said, in recent years, these fractional quantum Hall systems are experimentally observed. That makes them distinct from other theoretical proposals of anyons. Quite a few groups, as you can see on the right here, have independently seen these effects, which means a lot in this field, where sometimes some groups keep claiming things that nobody else can reproduce. Now let's turn to the anomalous Hall systems. They're called anomalous because, as observed very recently, there are certain two-dimensional crystals that exhibit a dual form of the fractional quantum Hall effect without there actually being a magnetic field. That's why it's called anomalous. In fact, there's a kind of duality. It turns out that something called Berry curvature over the momentum space of crystal momenta in the crystal plays the role of flux and position space. This is part of a duality dictionary, where position space gets interchanged with momentum space, flux density gets interchanged with a thing called Berry curvature. So that these systems are not so much one being the real, the other being the anomalous version, they're actually dual to each other. In any case, this has been observed rather recently, so this exists too. And here's a cartoon picture of the energy bands, the electron energy bands in these systems. The point being, where Berry curvature is concentrated, like our flux densities were before, there are little peaks in the valence bands. The valence band generally has to be flat for these fractional quantum anomalous Hall systems, but still has certain peaks. And at fractional filling, it means the peaks are holes where electrons are missing. But observe now, they are missing in momentum space. So this hole is a hole in momentum space instead of in position space. In any case, this suggests that fractional quantum anomalous Hall systems may be a viable topological quantum hardware. Viable in that it may be more practical than fractional quantum Hall systems because you don't need this huge magnetic field and the very low temperature that is needed for the FQH systems. Nevertheless, there's an open question, and has been, where and how are actually the anyons in these dual systems? Namely, what is observed in experiment is just the anomalous Hall effect, not the anyons themselves. So we know that these crystals do behave like FQH systems of sorts, but nobody has seen the anyons in them, and worse, nobody has had any theory or idea where actually to look for them. It's this theoretical aspect that I'm addressing here. Where and how are we to expect fractional quantum Hall anyons? So here's the answer in general. We just take a step back and look at the general theory of quantum systems, of parametrized quantum systems, and it gives a very clear answer where and how to identify anyons. So given a crystal symmetry group G and the Bloch-Hamiltonian space A, so the space of matrices, say, where our Bloch-Hamiltonians are allowed to vary by the nature of our crystalline material, then the topological phases are given by this formula, which I'm going to unwind in a second. Pi 0, the mapping space from the Brillouin torus to this Bloch-Hamiltonian space, and looking at G-equivalent maps. So step by step, why do we look at the mapping space? Well, that's the statement of Bloch's theorem that electrons in a crystal are described by this Bloch Hamiltonian, which is a map from crystal momenta to the internal degrees of freedom of the electron. So that's why it's mapping space. Why is it G-equivalent maps? Well, that's just the standard math jargon for what in the condensed matter theory is always given by this explicit formula, which says that in the presence of crystal symmetry, the Bloch Hamiltonian at a transformed crystal momentum is given by this conjugation action of some unitaries, which themselves depend on the given transformation. So this says nothing but that our map, that is the Bloch Hamiltonian, is an equivariant map. And finally, that we look at connected components, that's just the fact that we're looking at topological sectors. So we imagine that the system may fluctuate, the Hamiltonians, the Bloch Hamiltonians may vary, as you know, there's noise and heat in the system, but the topological property is the connected component that it cannot move out of, and that's what's computed by this pi0. So this also has some expression in terms of cohomology, which we're going to skip. So the examples are just to put us in perspective of what we're talking about here concretely. So these spaces A and usual systems that are, say, written by matrix Hamiltonians in lattice systems are Grassmannian spaces, where you have a quadratic matrix of length and width C plus V, and the assumption that there is a gap means some of the entries, V of the entries, correspond to valence bundle eigenvalues, the other C to the conduction band. If that is the classifying space we actually use, if we don't add any further bands to the system, or just take at face value the actual Hamiltonians we have, then one speaks of the fragile phase. Fragile because the homotopy type of this classifying space may change as we add more conduction bands. There are infinitely many more conduction bands in principle available to the system. If we allow our deformations to probe these conduction bands, we get a coarser classification. For instance, here, if we assume the valence bundle is a line bundle, but there's any number of conduction bands, then we're in the situation of Chern topology, which gives these fractional Chern insulators their name, that host these fractional quantum anomalous Hall systems. If we also take the valence bundle to be of arbitrary rank, then we're in the fully stable K-theoretic perspective. So going down here means we lose some information. We get a more robust but also coarser classification of the topological phases. And one key aspect that I want to highlight is that the magic happens actually in the fragile phase, which has previously not found much attention. So let's look at the topological order now. So the key claim now is that it's given by a similar looking formula, but pi0 is replaced by pi1. But where pi1 is the fundamental group, the group of loops in our space up to homotopy. And then we're looking at the irreducible unitary representations of this group. So why is that the case? Well, it is by the adiabatic, quantum adiabatic theorem in its topological version. The adiabatic theorem says that if you have a gapped ground state Hilbert space H, then they form a local system of flat bundle in the topological case over topological modular space. What does it mean? Well, suppose we're at some point in our topological modular space, we're somewhere here in the space of phases, and then there is a ground state Hilbert space associated to that configuration. Now, as we move in the space of topological band topologies, then the quantum adiabatic theorem says us that the Hilbert spaces will transform along by some unitary operators. As we keep moving, there's another unitary, there's compatibility conditions. As we move in a circle, these unitaries will have to satisfy some conditions. So that makes this assignment of ground state Hilbert spaces be a local system or flat bundle over the moduli space. But it also means, this is a standard mathematical fact, ancient fact, that we're equivalently looking at representations of the fundamental group. In each connected component, you can just reduce attention to paths that go in a loop. This is how this pi1 comes about. So this is why topological order, by the general properties of what topological order actually means, is controlled by pi1 of the band topology space. More precisely, it's actually controlled by, so configurations that differ only by diffeomorphism are actually physically equivalent. So we actually should divide out this situation by diffeomorphisms, and there's an action of the mapping class group on the result. But I'll skip over this for time reasons. So let's specify this now to the case of our fractional quantum anomalous Hall systems and fractional Chern insulators. So first of all, what's the Bloch Hamiltonian space? Well, we're looking generically for FCIs at two band systems, one valence band, one conduction band. The Bloch Hamiltonian is a map from the Brion torus to 2x2 matrices. So as such, it can be expanded in Pauli matrices. There's the global piece, which is irrelevant topologically. There's this relative bit whose norm gives the gap between the systems. So that's positive. The valence bundle is then just the -1 eigenvalue bundle of the normalized relative Hamiltonian, which means that the topology is really in this normalization. So you see we have 3 parameters. There's this positivity constraint we normalize. It means that in total, the space of Hamiltonians is actually just the 2-sphere, which is this Grassmannian. We have 2 bands, 1 valence band, 1 conduction band. So the band topology is actually given by continuous maps from the Brion torus to the 2-sphere. This is sort of known in the literature, even though it's maybe not often highlighted this way. So this means that the valence bundle is the pullback of the topological, the universal line bundle. Actually I'm going to skip over the top part of this diagram. Let's just, for time reasons, let's just look at the bottom part. So we just saw that here's our relative Hamiltonian from Brion torus to the 2-sphere. We can regard it as a map going all the way to BU1. So if we regard it as a map to the 2-sphere, we're looking at the fragile band topology. As we join all these conduction bands, we are looking at the stable band topology. Now the thing is, for topological phases, it makes no difference and hence it has been ignored. And the whole topic has actually been, the whole issue of fragile band topology has thereby been ignored actually, because it can be in this simple case. The topological phases are now characterized by an integer. So the homotopy class of this map here can either be regarded as being in pi0 of maps to the 2-sphere. That's, as such, it would be called the winding number, or it can be regarded as in connected components of maps to BU1. As such, it would be called the Chern number. Now, the Hopf degree theorem says that they, in this special case, they actually happen to agree. So in both cases, we just get an integer, and that is the usual Chern number that gives Chern insulators their name. So fragile topological phases are the same as stable, but this is no longer the case as we now look at topological order. So this sort of known what I'm saying here, even though maybe it's never been said quite in this way. But now we're looking at something that has not received attention before. So by the argument before with the quantum algebraic theorem, we know we have to look at pi1 of the space of these maps. So if we first do it in the stable case, as you might naively think should be the right thing to do for the Chern insulators, look at pi1 of maps to BU1. A simple computation shows that this is just the group of 2 copies of Z. In fact, this is the group of observers of the 2 Wilson loop observers around the 2 basic cycles of all torus, but in Maxwell theory, so everything commutes. This group has one-dimensional irreps, meaning that there's no topological order here. But, and this is the big but now, we observe that this situation changes drastically as we now put the fragile band topology in here for the computation of the monodromy. So we're now looking at pi1 of maps to the 2-sphere, and using results that date decades back in algebraic topology, one can show that this replacement of BU1 by the fragile space S2 deforms this abelian result to a non-abelian one, where there's an extra central generator shows up, which is exactly our breaking phase actually, that deforms the commutator, makes it non-abelian. So this is now the algebra of observables for Wilson loop observables on the torus for Chern-Simons theory, and that is the standard model. This is how usually Anyonic topological order on the torus is understood. Something whose quantum observables are given by exactly this formula. So see, this formula predicts there is the usual notion of anyons in FQAH systems, but now with the torus being the Brion torus. So these are solitonic anyons localized in momentum space. This is just what the math gives. On the other hand, one should admit at this point, this so far has assumed that all symmetries are broken. Remember, there was in general in our formula, there was a G here, the crystal symmetry, which is omitted everywhere here. Omitting it is the same thing as saying, well, there is no symmetry. The symmetry group is the trivial group. So this is the prediction of the theory for when exactly every symmetry is broken. Now we can also do the analogous computation in case that there are crystal symmetries. So let's compute fragile crystalline Chern phases. Apparently this has not even been computed before, even for the topological phases, let alone the topological order. So let's look at just one example to make it short. Let's look at P3 crystalline symmetry, 3-fold rotation around some point. So the topological phase turns out is given by an integer, which is the usual Chern number, and then there is a sector of a factor of 8 possible topological sectors, some finite set. How does this come about? Well, remember there's also an action of our group on the coefficient sphere, which in this case is rotation by an angle 2 pi over 3. And this has two fixed points. An equivariant map has to send fixed points to fixed points. So these fixed points, these three fixed points here in our torus, have to go to either of these poles, these fixed poles, and there's 8 such choices, 2 to the 3. This is this 8. So this is a new answer even for topological phases, but of course here we're interested in identifying the topological order, and the computation gives that the group of band monodromies here, including this covariantization, which I actually skipped over in the previous discussion, contains a copy of sim3 of the symmetric group on 3 elements, which acts like braiding the 3 high symmetry points around each other. For instance, there's one element in here, which is a pi rotation, which essentially rotates these two fixed points around the central one. In this sense, it braids the fixed points. So it's a non-abelian group. It regards the high symmetry points as defect anyons, and as such, actually, as parastatistical anyons, and that they're given not quite by a break group, but something in between an abelian group and a break group, the symmetric group. But this is already a rich group. For instance, the standard IRAP, unitary IRAP of sim3, contains both a z-gate and a rotation gate, which thereby would be topologically protected. So to conclude, fractional quantum anomalous topological order is theoretically seen by looking at the monodromy of fragile band topology. This gives clear predictions of what should be going on via computations in equivariant homotopy theory. The general picture is the band topology is maps to Bloch Hamiltonian space A. The topological phases are its components pi0. The topological order is essentially its monodromy pi1. For FQH CERN insulators, this classifying space A is the 2-sphere. When all symmetry is broken, it predicts there are solitonic anyons in momentum space of the crystal. If there's, for instance, P3 crystal symmetry, it predicts there are defect para anyons in momentum space. In either case, these are tantalizing targets for experiment to look for. Thanks for your attention.